The final problem we're going to do in section 12.3 on the dot product is sample question 21. It asks us to show that if two vectors x and y are perpendicular to each other, then the following statement must be true. The magnitude of x squared plus the magnitude of y squared equals the magnitude of x plus y squared. Now, drawing a little picture of these two vectors, we can get a sense of what this statement actually means. If this represents x and this represents y and they meet at a right angle, of course, vectors that meet at a right angle have a sum which just produces the hypotenuse of the right triangle that they comprise. So this would be x plus y. And of course, this then becomes the Pythagorean theorem. The follow-up question was, what is this really representative of? And of course, in this unique circumstance where we're adding the sum of the squares of two perpendicular vectors, of course, we're going to get the square of the hypotenuse. Okay, well, let's go about proving it. They ask us to use theorem 12.3.5, which is a multi-part theorem. We're not going to need all parts of it, but there are two parts we're going to use. Any vector that's dotted with itself, it's basically like squaring the magnitude. So we're just going to get the magnitude of the vector squared if we take the dot product of a vector with itself. The second part of theorem 12.3.5 we'll use is the fact that the dot product obeys the law of distribution. If I want to dot u with the sum of vector x plus y, then that's the same as u dotted with x plus u dotted with y. So let's apply these two theorems in the solving of this problem. I'm going to start it this way. I'm going to say, let's suppose we have the vector x plus y. And what we want to do is we want to dot this with itself, the vector x plus y. Well, according to the first part of theorem 12.3.5, this means that this will just be the magnitude of whatever vector x plus y is squared. So x plus y squared. But I can also apply this rule to go ahead and do the distribution here, and that's going to mean this will be x dotted with x plus x dotted with y plus y dotted with x plus y dotted with y. So if, as this part of the theorem says, the dot product follows the rules for distribution, then it produces these four dot products. Well, let's look above. X and y are perpendicular vectors, and I know for a fact that perpendicular vectors have zero dot products. That means these two inner products here are both zero. In addition, I'm dotting x with itself and y with itself. So the first part of the theorem says that those are just the magnitudes squared. So this statement should be the magnitude of x squared plus the magnitude of y squared. We've already proven that this dot product is equal to the magnitude of x plus y squared, so that completes our proof.